Okay, in this question we're asked to find the angle between two planes, and here we are given the Cartesian form of the planes. Okay, plane 1 and plane 2. So let me just draw a quick picture here. I'll try my best at drawing. It's always hard to draw 3D pictures. But there's my plane 1, and here's my plane 2. I'll try my best at drawing it. So it intersects this plane here, and keeps going. And there we go. So plane 1 and plane 2. And this line in here is the intersection of them. Okay, we're asked to find the angle between them. So what I really need is this angle here. We'll call it phi. Okay, so we're trying to find the angle between them. Okay, we generally take it to be the acute angle as opposed to this one over here, which would be 180 minus phi. So it's all related, but we generally just take the acute angle. Okay, so how do we go about finding the angle between two planes? And the trick is to realize that this is my normal vector to plane 1, which I'll call N1. It's coming out towards out of the screen. It's hard to draw. And plane 2, the normal vector lives over here. Normal 2. So if I take those two vectors, N2 and N1, the point is, I'll try my best to draw this. The point is, the two planes, if I rotate them 90 degrees, that's going to be the normal vectors, because the normal vectors are perpendicular or 90 degrees from each plane. So all I have to do is I have to find the angle between the two normal vectors, and that will be the same angle phi between the two planes. Do it. If you take two pieces of paper, put them at some angle, and rotate it 90 degrees, so we get the normals, the angle doesn't change. Alright, so we just need to find the angle between two vectors, n1 and n2. We know how to do that. Cos theta, or maybe I'll start with the dot product, n1 dotted with n2 is equal to cos phi, I should say, the angle between the planes, divided by modulus of n1 divided by the modulus of n2. So the question is, how do we find n1 and how do we find n2? So let's do that. So the beauty about the Cartesian equation of the plane, as we saw in the previous video, it's equal to r dotted with n, or n dotted with r, a dotted with n. And r is x, y, z. So all we have to do to get the normal is the coefficients of x, y, and z. It's as easy as that. So n1 will be 2, 1, negative 2. 2, 1, negative 2. Okay, because r dotted with n, r is the position vector x, y, z. So r dotted with n is just 2x plus y minus 2z. So therefore n is just the coefficients. I bet you can guess what n2 is going to be. Did you guys say 3, negative 6, negative 2? I hope so. Anyhow, that's n1 and n2. So let's have a look. We need to get, so we know what this is, we know what this is, we can work out the dot product, but we do need the modulus of each one. So the modulus of n1 is equal to the square root of 2 squared plus 1 squared plus 2 squared. So each component squared, and we can ignore negative signs because they're getting squared. Modulus of n2 is 3 squared plus 6 squared plus 2 squared. So this is equal to 4 plus 4 plus 1 is 9. Square root of 9 is 3. And the square root of 49 is 7. That works out nicely. Okay, so therefore the dot product of n1 and n2, which is 2, 1, negative 2, dotted with 3, negative 6, negative 2, is equal to cosine phi, the thing we're trying to solve, divided by 3 times 7. Okay, 3 and 7, so I'll put a times in there. So, therefore, let's take the dot product. 2 times 3 is 6, plus 1 times negative 6, which is negative 6, minus 2 times minus 2, so plus 4. 6 and negative 6 cancel to give me 4, and that's equal to cos phi on 21. So, therefore, cosine phi is equal to 21 times 4, which is 84, and phi is equal to arc cosine of 84, or inverse cos, and we'll leave it like that. You always want to give an exact value. There's no calculators allowed, so you just want to give an exact value, and that's perfect. So phi, the angle between the two planes, is equivalent to the angle between the two normals, which is arc cosine of 84. So have a go at question 2b, and hopefully you can reproduce the same result.